Hello everyone, my name is Jan, and today I'm going to be talking to you about side channels. So this is a topic that's a little different from the other topics you encounter in this course, but I hope you find it nevertheless interesting. So let's start with this picture. It depicts a real-life side channel, and just try to figure out what we see here. What happened here? Well, for those of you who don't get it already, there's a picture posted by the police. There was something illegal going down in that house. And this is actually in the Netherlands. Yeah, obviously this was illegal marijuana plantation. And the heat from all the lamps of the equipment actually is visible in melting the snow on top of this house. And that's how the police was able to spot that house, even though the plants itself weren't actually visible from outside. And this brings us to an issue with our view of cryptography, because usually we think of cryptography as some complicated math that is plugged into each other, and then you have a mathematical model with messages going back and forth between communication partners, and then some attacker that is able to observe those messages to inject malicious messages himself. And you get an attacker model that quantifies what exactly the attacker is able to do. And then you get some security proof that says, okay, the attacker cannot gain his advantage in a security game, for example, and therefore this system can be considered secure in the setting. The issue with this view is that just as with the house, there's ways that information about the secret state of the communications partners, or the secrets of what's going on inside the house, can leak to the outside world. So the fundamental difference between mathematics and the real world is that people have to create programs that implement this cryptography. That's often difficult to do, and it's sometimes it's difficult to get it right. And even worse, we have to run this on electronic devices. Everybody has a smartphone, a laptop, but all those electronic components inside can lead to some very interesting ways to leak the information. So for example, through electromagnetic radiation. If your computation has some current running through a cable, then if you have a sensitive enough antenna, you can pick that up. So this is a way that the secret information can leak, even if judging by the mathematical model, everything is fine, everything is secure. And the way you use this, either as an attacker or as somebody protecting against this, is to first find some way in which your software or hardware has behavior that changes on some secret state inside. If your software or your hardware is always doing the same thing, then it's obviously not useful, but it also doesn't leak any information. But if you have something that depends on a secret state, then it can also happen that this change in behavior of the software or the hardware is then visible to an outside observer through various means. If you have identified one of those means, then you need to kind of describe it mathematically, what really the information is in a mathematical sense, and determine what input, what modification to the messages you need to do to get the most useful information from your side channel. And if you are successful at that, then you can come up with a way to just do this over and over again, and just by disclosing some information, maybe just a few bits about the secret state, but by repeating it, you can disclose the entire secret. Now, the step after that really depends on what your ethical stance is. So if you're a white hat, if you're one of the good guys, so to speak, then of course you should inform the vendor, the programmers of that software, the vendor of that hardware, that there is an issue, that they need to take care of this before somebody abuses it. If the vendor happens to have a bug bounty, for example, then you might even make a profit from this. There have been very generous bug bounties reported for some of the vulnerabilities I will talk about in this lecture. So we're talking 5 figures here, not something you sweep under the rug. And then in the end, if you're in academia, then also just publish this, get some fame, maybe also some funding, and you're good to go. If you're not one of the good guys or don't have so many issues with how your findings are used, then you can potentially sell this to the NSA or another, let's say, more openly criminal organization. And they can then use that to maybe get information about somebody they're really interested in, or maybe they're interested in everyone and they just use it on everyone. You don't get to choose afterwards. So the following lecture will not be about which decision to make here, but instead I'm going to be focusing on 2 attacks that I'm going to present to you. The first is Manger's attack on RSA padding mode, called optimal asymmetric encryption padding. This is kind of straightforward, rather easy to understand. A similar attack, which is Bleichenbacher's attack, and its impact it had on the crypto industry as a whole, on standard bodies and etc. And then we're going to be talking about the actual side channels that you have, because different hardware behavior, like electromagnetic radiation or timing attacks, will all work to disclose maybe similar or maybe different information depending on what you have. So it's very important to also be aware of in which ways you can leak information. So because this is a rather hands-on lecture, you also get hands-on exercise. And in order to prepare for that, I have also prepared a video where I walk you through the software and the tools we're going to be needing for the exercise. And last but not least, I'm going to be giving you some very practical hands-on advice on how to design or how not to design a cryptographic system, how to do programming, and then also an outlook into the future. With that said, let's go. So, welcome back. Now let's take a look at optimal asymmetric encryption padding. So we'll go through the padding first, and then in the next video I'll show you the tag that can be mounted against it. So what's OAEP in the first place? It's a padding algorithm used for RSA. It's standardized as PKCS number 1 version 2.0, and it has a very big advantage over some other padding schemes in that it's provably secure against active attacks. If you're interested into the intuition or the actual proof of being able to resist active attacks, then you can go to these links I put on the slide. But why do we need a padding algorithm in the first place? To see why we need that, we have to take a look at how RSA encryption works. So this is the infamous RSA encryption. You should remember this from the crypto recap done by Tibor. But suffice to say that you have some modulo n that's composed of 2 primes, And then you have an decryption exponent and an encryption exponent named D and E respectively. So the secret key is composed of the modulo and the decryption exponent, and the public key, the one that you give out to the world to see and use to encrypt messages to you, is composed of the modulo and E. Now, encryption is just take a message, raise it to the public encryption exponent, take the modulo n, and you get your ciphertext. And decryption then works as take the ciphertext you got, raise it to the power of your secret decryption exponent, modulo n again, and you arrive by the power of math at your original message. Now, this construction has some very interesting properties, and one that will be used by the attacks I'm going to present to you is the multiplicative homomorphism. So essentially it says that if you encrypt one message, you get a number, and if you multiply that number with the encryption of a second message, then that's the same as encrypting the both messages multiplied. This is a result of m raised to the power of e times m2 raised to the power of e being the same as multiplying both first and then raising them to the power of e. But that means that even if we get access to some ciphertext, then we can do multiplications on it, even though we don't know what the ciphertext is. We can still say double it, modulo n, of course. And that's something we will be using. Another issue with this is that if you take, for example, the number 0, if you encrypt it, you get 0 again. Take the number 1, encrypt it, you get 1 again. And for very low numbers, actually the result of the encryption can be easily reverted. So this scheme only works if your message that you're encrypting is about the same size as your modulo n, like your key. And that, of course, is an issue because you want your encryption system to work on arbitrary messages. And sometimes you maybe want to transmit a 0 or just a 1. And for that, you kind of just add extra data to your message so that that the result of it is long enough to be able to be encrypted securely. Another reason you need padding is that if I take the same message M1 and encrypt it using this textbook RSA mode twice, then I get the same ciphertext. So it's easily distinguishable by an attacker if two messages are the encryptions of the same plaintext. And for that you want to add some randomness, something that makes sure that even though I put the same message in twice, I will get different ciphertexts, that an attacker is not being able to determine anymore whether those were the same. And one algorithm that achieves that is OAAP. So it does both. It creates an output of the desired length, namely how many bits are in your RSA key, and it also has some randomization in it. So let's go through it from top to bottom. We start with encoding some message M. We add zeros to the end of that message until we have the desired size. And some part of that is also randomness. So we come up with some good randomness and feed that randomness through a hash function, G. The output of that hash function is then XORed with our message concatenated with the 0 padding, and that output is X. It is fed back through a second hash function, H, and XOR to the randomness R to produce Y. So you might be asking yourself, why are we doing all of this? Well, after going through the two hash functions, what we get out at the bottom, x and y, those are of the appropriate length. And because r is random and it goes into both the inputs of x and the inputs of y, the message will be indistinguishable from any other message, even if it's the same input m, because the randomness r will be different. Now, if you say you want to decode such encoded message, so you take x and y, you concatenate it and put it in an RSA, encrypt it, and the receiver decrypts that, splits it back into x and y, and then it does essentially the following: it just reverses the process, takes x, passes it through the hash function h, XORs it with the y to recover the randomness that was being used, and that is then fed back through hash function g, XORed with x, and then what you end up with is the original message, concatenated with the zeros that you can then strip off the message and discard. So why is this construction secure? Why can we construct a security proof? Well, just to give you an intuition, after the RSA decryption, I need to be able to get every single bit of x and y, otherwise I will not be able to get the message m or r or anything, any other information about them. The reason is the following. Consider a single bit that I missed, that maybe the attacker was not able to get right, and that bit is flipped in x. By going through the hash function h, the output of h will change dramatically. This is one of the core properties of a hash function, that even small changes in the input will have a huge impact on the output. So after going through h, the output of that function is essentially garbage. It has nothing to do with what the output of h should be if x were correct. By that being XOR to y, you recover essentially an almost entirely incorrect r. And that is being fed back through g, and in the end XORed with x. And if the randomness is total garbage, then you can already see that also the message and the padding you try to get out of x will be garbage as well. If there were a single bit flip in y, then you can see that the randomness we get out of there is almost correct. One single bit flip in y will only affect a single bit in r that we recover. But that single bit is still enough to change the output of g entirely. And since that is XORed on x to recover the message m, the message itself is still protected and cannot be recovered. So that essentially is the intuition why this is a good padding algorithm that protects the message and every single bit of it. Now, this padding algorithm was standardized under the name PKCS number 1 in version 2.0. So I put a link to the standard down there if you want to have all the gory details. This is just a small diagram of how it works in the standard, and you probably are very you don't know what really is going on, because what I've just shown you looks so different from this diagram you're just seeing. But let me walk you through this, and then you'll probably see that what is shown here is actually pretty much the same. So by putting the familiar terms I used in the previous slide on top, you can already kind of see that the arrows, the XORs, are pretty much the same as we have just discussed about. The hash function in this standard are called MGF, or mask generating function, because they produce variable size output, not like a usual hash function that produces a single size output. But in how it's done in the real world, this is still using a hash function under the hood. It just modifies the output of the hash function after it gets it to make it the proper size. So this is the mask generating function instead of the hash functions. Then your randomness R is called the seed. The padding and secret are what we talked about as the zero padding, and the secret essentially is the message we want to encrypt. And then our plain text we get out of our RSA decryption is composed of path X and Y, which are not explicitly marked in this diagram. Now there's some extra stuff here that you can see. On the top you see that there's some additional hash that is kind of compared to something that's inside the message together with the padding. And the purpose of this is to kind of being able to send along additional data that is not actually encrypted, but that is tied to the message. So the message, like this additional data, is hashed, and then when you receive the message, you decrypt the actual ciphertext to the plain text. You do all this depadding, and in the end you end up with hash prime, and you that hash prime is cryptographically protected, and then you can compare that hash prime over the hash of the data you got, and then you can see whether that data has been modified. And last but not least, in the top bottom you see 2 zeros, and that is to ensure that the plaintext you put into the RSA encryption is not bigger or as big as the key, as the modulo n, because if it were, then it would be mathematically impossible to recover the original message. So the message has to be smaller, and to ensure this, they said, okay, let's just enforce 2 0 bytes at the beginning of the message, and that mathematically makes it smaller than the key, which is full size. So let's take a look now at Manger's attack on OAAP. Now, this is how OAP is standardized, what we took a look at in the last video. And let's try to spot the issue with this construction. Don't see it yet? It's this small, almost insignificant detail of starting with 0, 0 over there, which was introduced to make sure that the message is smaller than the modulus. If you were to implement this decoding of the RSA decryption result to recover the original message, how would you do that? For example, if you were writing a web server. Of course, you get this, you first check whether it starts with 0, 0, and if it doesn't, then you give the client that is accessing your server some error message that it did something wrong, where this message should start with 0, 0, and what you gave me did not. And then you do all this hash generation stuff, and then in the end you have your message, and then you process it in the actual server software. Now, by doing something like this, you have created a side-channel oracle. Because now an attacker can send you a ciphertext that it doesn't know what the decryption is, but you're essentially telling him in the case that it starts with 0, 0 by processing it further, that it started with the 0, 0, and in the case you give an error, you're telling the attacker, well, this did not start with 0, 0. And this means that you get an attack scenario where the attacker records something that is RSA encrypted and OAP padded, and then doesn't need to be immediately afterwards, gives you some modified messages. You being, for example, a server, just reply either saying your padding was wrong, it didn't start with 0, 0, or instead saying what you're saying is nonsense, because in a later step the processing will most probably fail, because the modified message is not actually containing anything meaningful. If you put this into mathematical terms, you've created a padding oracle. So again, if you have a RSA modulus n, public exponent e, private exponent d, and you have a key of size in byte k, then we define a capital B, which is 2 to the power of 8 times k minus 1. So this is essentially just the first number of which the or the last number of which the byte representation is starting with 0, 0 or 0, 1 respectively. So B in itself starts with 0, 1 and is then zeros. And every message that conforms to the padding, that starts with 0, 0, is smaller than B. Now, the attacker knows the public key, so N and E. He captures the ciphertext by sniffing on the network, and then tries to find the plaintext corresponding to it. The oracle will help him in that, because for the input X, it decrypts X by raising it to the power of the private D, and then it will check whether the result of that decryption starts with 0, 0. So either in case it starts with 0, 0, we reply with Y is smaller than B, or Y is greater or equal to B in case it doesn't start with 0, 0 and the movement of the padding was not successful. Now the intuition behind this attack is the following. Every time the oracle replies, you kind of get information whether or not the decrypted message was smaller or bigger than B. And that tells you that if you take an F times the ciphertext you get, encrypt the F and send that to the oracle, it will decrypt that to F times M and then tell you whether the result of that was smaller or greater than B. Now, to make an efficient attack, you try to pick your F in a way that you already know beforehand by knowing some constraints about M, that the result of that will be between 0 and 2B. And by replying, the oracle either tells you it's in this left half between 0 and B, if the padding was correct, or if it complains about the padding being incorrect, you know that the decoded message F times M was between B and 2B. And by just doing this over and over again, you can kind of shrink down the range of numbers that M could have. And in the end, you're left with a range of with 1, which contains exactly M. And at that point, the attacker is successful because it now knows M precisely, just by asking whether or not different messages were correctly padded. So what does the actual attack look like? We proceeds in 3 steps. So again, we intercept our RSA encrypted and padded message. And then after executing the first step, asking the oracle several times, then we find out that M lies in the range B divided by sum F1 and 2B divided by sum F1. So the F1 is the output of the first step. In the second step, we output F2, and there we already know more about the range. So the output of the range outputted by step 2 is even smaller. And then by taking that as the input of step 3, after some time it converges towards a single range that only contains one value, and that is then the message itself. So how does the actual step 1 work? Don't worry if you don't understand all the details. I'm just trying to give you an intuition that all this complicated math in the end is not rocket science, but it's actually quite easy and also quite easy to implement for an attacker. So you remember your oracle, which just tells you whether something is correctly padded or not. So it tells you whether the decryption result is smaller than B or greater than B. And you start with F1 equals 2. You already know that the message you intercepted was between 0 and B, simply because the message you intercepted was correctly padded. And if you now take that F1 you choose, which is 2, raise it to the encryption, multiply that with the ciphertext you intercepted, and send that to the oracle. The oracle will decrypt that and decide whether F1 times M is smaller than B. If it replies that it was smaller than B, then you know that your that F1 times your message was in the interval 0B, or otherwise it was in the interval B and 2B. So either in the left half or in the right half of the interval. If you are still in the left half of the interval, then you double your value of F1 and try again, so long until you are in the interval B and 2B. This way, at the end of step 1, we learned sum F1, for which F1 divided by 2 times M is in the interval B half and B. So we now have an interval that is smaller than the one we started with. And we can use that knowledge now for step 2 to decrease the possible interval even further. In step 2, we pick our F2 in such a way that our F2 multiplied with the message is in the interval n half and n plus b. We do the exact same thing, raise our F2 to the power of e, multiply with the message we intercepted, send that to the oracle, and the oracle will gladly tell us whether the F2 times m is in the interval n half and n, or in the interval n and n plus. So again, either it's in the left half or in the right half. Keep in mind that we're always calculating modulo n over here. So actually, if the message modulo n is in the left half, then it is bigger than b. And if the modulo n is in the right half of the interval, then it is smaller than b. Because n modulo n, if you take a look at the range n and n plus b, the n modulo n is 0, and n plus b modulo n is b. So that is the interval 0 to b, whereas in the top interval it is b to 2b, if we think of it in terms of step 1. But it's pretty similar now. We either increase our f2 by f1/2 in this case, and then we repeat this process until we know that f2 times m is in the interval n and n plus, which is smaller than the interval we started with, and it is then used in step 3 of the attack. Now, step 3 may look intimidating at first, but let me give you an intuition of what's going on here. We start with the knowledge that f2 from the previous step times m was in the interval n and n plus b. If we divide by f2, we know that the actual message is in the interval between n divided by f2 and n plus b divided by f2. We now save this in a minimum and a maximum value for the message. So we know that the true plaintext message must be a value somewhere in between those. We tried again to hit a point so in the middle, so that we halve an interval, and that point is f3, except that for rounding reasons and other reasons, you need to take some intermediate value, which is approximately f3, and then figure out a way for getting the exact value of f3, which then for which you then know that f3 times m is in the interval I times n and I times n plus 2b. So there's this sum I, but since we are doing all of this math modulo n, we can already see that this interval equates to f3 times m being either between 0 and 2b if we're doing modulo n. And then we send that message to the oracle, and we get back whether the message is in the left or in the right half. So either between in and in plus b, or between in plus b and in plus 2b. And then we either set our minimum value to be that breakpoint in plus b, or we set the maximum value. So we kind of shrink our interval either to the left or to the right half of what we had before. And then we go back to the previous step and do this over and over again, shrinking every time our interval of possible values of m to half of its size, either the left or the right half. And at some point we reach the step where our minimum value and the maximum value for our message is the same. And at that point, we have converged to an interval of size 1, and we know, okay, m min or m max, both being equal, are exactly the message, the plaintext message. So we have successfully decrypted the ciphertext and recovered the plaintext. So I hope you have now an intuition of how the attack works, how the information about the message, even though just very small, just being whether the message is smaller than b or greater than it, can be used to shrink down the range of possible values of the plaintext message to 1, at which point you have recovered the original message. And this brings us back to our main question of security and how it fails even though a provable security scheme is used. So you have seen now that if such an oracle is available, then the security proof can kind of be circumvented. So just some information on the plaintext structure and giving that to an attacker can be too much, because the attacker can just repeatedly access the oracle and therefore narrow down the range. And such oracles are not very common if you are thinking, for example, about email encryption, because you would have to get that recipient to reply to a malformed email repeatedly. But if you're thinking about a web server, then this is readily available. They will just reply to you, even if it takes you 1,100 queries. And this is actually the number of queries required approximately if you want to break 1024-bit RSA. And even for what is now considered to be still reasonably secure 2048-bit RSA, you still only need 2,200 oracle queries roundabout. So if you're interested in the full detail, or if something is still unclear to you and you want to read more about it, then visit the URL you can see now. And over there you can find the original paper by Manger. It's almost 20 years old now. But you will also need this for the exercise. So it's a good idea either way to download it and take a look at it. So let's come to Bleichenbacher's attack. Bleichenbacher's attack is very similar to Manger's attack, and you will see why that is the case. But first, we have to look at the padding algorithm that Bleichenbacher's attack applies to. So you have seen OAEP before, which was standardized as PKCS number 1 version 2.0, and this padding algorithm version 1.5 is a predecessor of that. It does not have such a nice security proof, and it is very simple. So you see that we again have a message, and for padding we now use random non-zero bytes as much as required. And then we have a delimiter between the padding and the message, which is a 0 byte, and 0 byte at the beginning, similar to the OAEP byte that enforces that it actually fits into the RSA modulus, and then a 0.2 byte, which is used for some kind of version number, since it's just used in PKCS 1 version 1.5, this is always just 0.2. And then we now put this message into, no, actually we don't. This is the whole padding mechanism. There's no hashing involved. It's just adding these random bytes and the 0 bytes and 2 bytes. Now, this is very straightforward. And as you can imagine, there's no simple security proof, as is the case with OAEP. But that is also the reason why it was replaced in version 2.0 with OAEP in the first place. So if you've seen Manger's attack, then you can probably already spot what the issue is with this padding type. Well, of course, it's those pesky 0 bytes and the 0.2 byte. So to come back to the Oracle scenario, this time we get an RSA encrypted but PKCS 1 version 1.5 padded message. You intercept that, you send modified messages to Bob or the server, and again he replies with whether the padding is wrong or whether the padding was correct. The Manger padding oracle, where you only got the reply if the output started with 0. And we can pretty much keep this definition for Bleichenbacher, except that now our B is 1 byte shorter. And now, because the output needs to start with 2, we know that the output needs to be bigger than 2B. And because it cannot start with 0003, we know that it needs to be smaller than 3B. So that's all that changes, and it essentially captures that a correctly padded message has to start with 0002. Now you might be thinking, wait a minute, after that should come some other random padding and then a 0 delimiter and then the message. But it turns out that many implementations don't actually enforce that. They just take a look at 0002 being there, and if it's there, then the padding is probably fine, right? So the idea between Bleichenbacher's attack is essentially the same as with Manger's attack. You still have your f that you choose wisely. You raise f to the power of e times the ciphertext you intercepted, mod n, send that to the oracle, and it will tell you whether f times m is between 2b and 3b. That you can use to kind of determine the interval that the real plaintext message is in, but instead of having one minimum and one maximum, as we had with Manger, especially in step 3, Bleichenbacher's oracle and Bleichenbacher's attack require that you use a set of intervals, because your interval will not be evenly split in the middle, so you end up with more chunks, more intervals after getting a reply to an oracle. But in the end, it's the same idea. So you can kind of narrow down the range of possible values. So you get several intervals, but those will be even added together will be smaller than the interval you started with. And then you still have to try a large number of f. And every time you get something that is that conforms to the padding, you reveal a lot of information. If you don't get that information, it's not that helpful. And because you now have to randomly hit 0002, for which the probability is lower than hitting, say, 00. So because you have to get lucky in hitting 0002, it also takes more oracle queries. So this is the reason why this message was also nicknamed the million message attack, because in the original version, as Bleichenbacher put it, it took about a million messages or oracle queries to be successful, although this varies widely depending on how lucky you get with the f's you choose. And then afterwards, there were also works that were able to improve this by several orders of magnitude by choosing the f in a more clever fashion than the straightforward way that Bleichenbacher put it. But that's all just maximizing the success probability of each oracle request. And then in the end, you can get away with a few tens of thousands oracle requests. So now that we've seen how Bleichenbacher's attack works, let's take a look at the impact it had and how it works in a real-world scenario. So to illustrate the following, let's take a look at what happened when. So back in 1993, PKCS number 1 version 1.5, the one that is susceptible to the Bleichenbacher attack, was first standardized and published, but Bleichenbacher's attack back then was not known. Then in 1995, we got the first version of SSL, which since has been renamed to TLS. So that's the crypto technology you've already heard about underlying HTTPS. And SSL version 2 included PKCS number 1 version 1.5 padding, both for signatures and for encryption. And then in 1998, in August, Bleichenbacher published his paper, his seminal paper, outlining his attack and how he uses the oracle created by PKCS number 1 version 1.5. So how does this attack actually look like? In TLS, you get first an asymmetric encryption handshake, where a symmetric key is transferred from the client to the server, agreed upon, and that key is then later used to encrypt the actual application data, because it's much more computationally expensive to do asymmetric crypto. So you just do asymmetric crypto once to exchange a symmetric key, and then you can do the efficient symmetric crypto to encrypt and protect the actual application data. Our adversary listens in on both the handshake and the exchange data and records both. The RSA encrypted symmetric key is then used as the ciphertext that he is trying to attack with Bleichenbacher's attack. He runs that against the server, because the server will reply to his oracle queries. And once he has decrypted this encrypted symmetric key, he then uses the symmetric key to trivially decrypt the actual application data that was exchanged. So this is a little different from the attack I outlined earlier, because after decryption we still have to use the key we got to then go on to decrypt the actual application data, but it doesn't make the attack itself any more complex. So in September of 1998, PKCS number 1 version 2, which specified OAEP, was released, and that one worked better. Well, we know that there's Manger's attack for that, but at least it has a security proof, and it's a little easier to get right than the PKCS number 1 version 1.5 padding. So you'd think that when they released TLS 1.0, which is the updated version of SSL2 in 1999, they'd include the updated version of PKCS padding. Except they didn't. They did the very reasonable thing, and instead of fixing the crypto that was broken, they just put wording in the document that told implementers, oh, by the way, there is an attack, and you really only need to make sure that you don't leak an oracle accidentally. So all you need to do is, if you get an incorrectly formatted message, reply the same as if you had a correctly formatted message. Straightforward, right? So that's what was put into the standard in 1999. And in 2003, after everybody had fixed their TLS implementation, apparently, Klima came along. And he noticed that by removing the padding oracle, some implementations had actually created a new one. What had happened? So this is the PKCS padding as you know it, that is susceptible to Bleichenbacher. And the new TLS version mandated that also the version number should be checked, because it should only be that a TLS server using TLS encryption should respond with TLS to a TLS request, and not with an older version. So the version number of the TLS protocol to be used had to match. And that essentially means that the first 2 bytes inside of the message should be consistent with what the server was expecting from the client. In the case of TLS 1.2, those bytes would be 0303. And you can already see that this actually opened up another side channel, because now the server would tell you by either going, you provided an incorrect TLS version number, or okay, your TLS version number is correct, I'm going to go ahead. It provided another side channel that could be abused with a modified attack. But the idea of getting some mathematical information about the secret ciphertext is the same. So when they published TLS 1.1 in 2006, they took care of this. They added another section, so right down at the bottom you can see a note that if servers choose to check the version number, they should randomize the pre-master secret in case of error. And don't reply with an alert in order to avoid variants of the Bleichenbacher attack, particularly Klima. And then they were very sure that no implementation was vulnerable to Bleichenbacher anymore. They said no variants of Bleichenbacher attack are known to exist, provided that the above recommendations are followed. And those are the recommendations that you've already pretty much seen before to treat the errors as indistinguishable. Some time went by and TLS 1.2 came out. And you think, oh, maybe they actually saw that out there some implementations were not checking the padding correctly. And it seems they did. But instead of choosing a better padding scheme that was not as susceptible to errors in checking, they instead did this. Well, you can already see it's getting a little complicated of what your implementation has to do in which case of which failures. And they actually provide an algorithm, like those two are outlined in bold, what you have to do if you want to check the version numbers or don't want to check the version numbers, and when you have to generate some randomness to replace for the message. And yeah, there's 2 of those, because for some reason the second one is theoretically not secure, so only the first one is recommended. But still the second one is also in the standard of you could still do it this way if you want. And then there is still a reassuring thing that like, if you do it like this, then everything is fine. And then when 10 years later TLS 1.3 came around, they finally did what I think is the right thing. They removed it altogether. So they don't use RSA encryption anymore. They don't use PKCS version 1.5 in that context. So now this note has been moved to the appendix, and there they say, okay, we are no longer susceptible to the Bleichenbacher type attack. But they add a note that still you could be attacked if your server still supports TLS version 1.2, which pretty much every server does, because not every client has received a software update since 2018 that would bring it, that would make it compatible with TLS 1.3. And looking at some older Android phones, there's probably also a large number of devices that never will get an update. So where does this leave us? In 2018, there's almost 2 decades now of Bleichenbacher attacks, going back to 1998. And it seems that with TLS 1.3, this whole Bleichenbacher thing has finally run its course. It's been removed from the new standard. And it's been so long a time, and there's so much information, even in the standard, about how to avoid the Bleichenbacher attacks, that this is now finally done. Which is what a lot of people assumed. OpenSSL, the most widely used TLS library, was not vulnerable anymore. That was the library that Bleichenbacher's original attack had been published for, that he had abused. And that one was fixed. And so everybody was told, okay, the other open source libraries they checked are also fixed, and the commercial vendors, they already fixed that long ago, right? And the question is, it's not only TLS that uses PKCS. It's also included in the X509 certificate standard. It's also used in email encryption, as MIME and PGP. It's used in IPsec, and for good measure, it's also standardized as an encryption mechanism in JSON and XML for encrypted web services. So those are not as regularly updated. So there's no XML 1.3 that updated this to bring us up to par with TLS standard. So those will probably be vulnerable for some more time. And even more, let's take a look at what was still vulnerable back in 2018, when some security researchers thought, okay, let's check whether everybody actually fixed this. And they scanned the most commonly used websites. And the first hit they got was facebook.com. It's one of those unknown pages that has no confidential information in it, so an attack over there would not be a big danger. And this was because they, like Facebook, patched OpenSSL for their own servers in a weird way, and that made them vulnerable. And then they looked further, and they found Cisco.com. It turns out that Cisco has some TLS appliances, some boxes that do your TLS decryption for you. And those were older, out of support devices, but they had a Bleichenbacher oracle on them, and they were still being used frequently across the web, and also to serve Cisco.com itself. And then there were some pages like eBay.com, PayPal, the account services subdomain of Microsoft, Web.de, like no big players in the market, right? And it turned out that F5, also a vendor of these TLS appliances, also did their error handling incorrectly in all weird different ways, in different product lines. And those were used by a lot of very big companies that were serving web pages with a lot of traffic. But it was not only F5 that were susceptible to Bleichenbacher attacks. It was also the Citrix Nextscaler line and the Radware Altians. And Palo Alto Network OS, the IBM GSKit, Wolf SSL, and the TLS library included in the Erlang programming language, as well as Bouncy Castle for Java, Unisys, ClearPath, the Symantec product lines, Cavium, and the FortiGuard SSL Deep Inspection and VIP SSL. And for good measure, there were still known vulnerable Java SSE and Matrix SSL versions out there that had already been spotted before, but for which some of the web administrators apparently did not bother updating the system. So that is pretty much all fixed now. Maybe not. you could go out there and check. And I think this tells us a lot about how serious some of these vulnerabilities are taken that can have a very high impact on the security of your internet connection. So, to put it in numbers, they found that 27 of the Alexa top 100 sites were vulnerable in one way or another to Bleichenbacher's attack. And 2.8% of the top million web pages were vulnerable. The only reason why not more were vulnerable was because OpenSSL is so widely used, and OpenSSL turned out to be actually fake. So, welcome back. Let's talk about side channel types, shall we? Now, you've seen how to exploit an oracle using, for example, Manger's or Bleichenbacher's attack. But how do you get this information? For Bleichenbacher's attack, that is mostly either error messages, network metadata, or timing. What exactly that entails, I'll get to in a minute. But there's also other attack vectors that have been exploited, and that is, for example, cache, because you can monitor the cache accesses of another process running on the same CPU. It's power consumption. If you can measure the power consumption of a device fine-grained, then you can kind of deduct which instructions have been executed. There's electromagnetic side channels, where you can observe from a distance using an antenna what computations were done or what data was transferred between different chips on a device. There's a classical optical attack, and more esoterically acoustic attacks. So let's start with error messages. We've just seen how many TLS libraries were still vulnerable back in 2018 to the Bleichenbacher attacks. And when the authors of the paper looked at these libraries, they found that they had all weird ways in which they were responding to the messages. So whether it be a correctly or an incorrectly padded message. And among them, they found 6 different TLS errors that they were able to get as a response from different TLS libraries. So if you have one library that responds with different TLS errors, then that can be used to easily distinguish a valid from an invalid padding, even over the network. And there's also network metadata that can be used to do the same. So this is not the actual error message itself, but also how the connection is aborted in the case of an error. So there's different ways to stop a TCP data transmission session that is underlying the TLS protocol. So there's a finished message, or you could just have a TCP timeout, so no reply at all, or a TCP reset, which says, please restart the session. There were cases where they got a TLS error message, but in some cases they got it only once, and in some cases they got it twice, so right after each other, even though that is not in the TLS spec at all. And some TLS library decided to reply with a change cipher spec message to kind of recover from that situation, even though that is not in the standard at all. So you really shouldn't be doing that as a response to invalid padding. So this covers the error messages. Of course, for other protocols and other situations, you encounter different error messages, and also other ways you can detect differences over the network. But I think that's just a good illustration of how the inconsistent behavior in face of an error can be leaked to the outside world. And then there's the big area of timing. So there's also these attacks on Bleichenbacher type oracles, where either you abort early after getting an incorrect padding, or you continue on processing and still get the same error, but maybe later. So you can kind of measure the time between sending the message and getting a reply, and if that time is shorter, then the parser aborted earlier in the decoding process. But there's also other algorithms that timing sidechannels apply to. For example, RSA can be sped up with a neat math trick called Chinese remainder theorem. So it actually gets you a speed up of 4. And then you can use square and multiply instead of exponentiation. But that speed up comes with a cost, because you get once in an exponent that will translate to multiplying and then squaring a number. And if you get a 0 in an exponent, you get only squaring. So you can already, from measuring the response time, you can determine how many ones are in the secret key element. And more sophisticated attacks can then be mounted to determine the entire secret key. One issue that has also been around for a pretty long time is hashed user passwords. So if you are doing the right thing and don't save the passwords of your website users in plaintext, but instead you hash them to make it more difficult for an attacker that hacks your database and gets all the passwords. So you don't store them in clear text, but instead you hash them, which is a good thing to do. But if you now get a request, you get a username and a hashed password, and you compare that to your database, then the efficient thing would be to first look if the user exists, and only then comparing the hashed passwords. But that essentially lets you determine which user names are actually existing on your server. So it lets you enumerate the registered users just by sending a request with a wrong password. And depending on whether the reply was very fast, you know that the user does not exist. Or if there was still an error, but the request took longer, then you know that the server did the hashing and then compared the passwords and then only returned an error to you. And one other programming issue that should be avoided is using the exception handler in languages like Java to handle your error cases. Because even if you return the same result code, the exception handler takes some time to start up, to create all the classes it needs to handle your exception. And even if it's caught later, that still means that there's some additional time needed to process that exception. So that is something that has already been an issue in the wild for matrix SSL that I've talked about earlier, I guess. So you find this in the Usenix paper at the bottom. So that is also a bad idea to rely on exception handling for those error handling where you don't want to leak any timing information. Then using the exception handler makes a big difference. And then there's all these nice little cache attacks. So you have a setting where the attacker is running on the same CPU as the server or the victim. And he evicts the instruction or the data from the cache by filling it with his own garbage. So because they're using the same shared cache, it can only either be the attacker's data in the cache or the victim's data in the cache. So you can kind of force, by tricking the CPU into putting your memory at the same place as the victim's cache stuff, you can evict the victim's data from the cache, so it's dropped. And when the victim now tries to access that data, he has to load it from RAM again. So the response will be slower. Then you can detect whether or not this memory location was actually used by measuring your own access time. So if you read your own garbage at a later time, if the victim has been using the same cache, then his entry will be there and your request will be slower. Or if the victim hasn't been using it, then your entry will still be in the cache and your access time is faster. So this has been used for all kinds of attacks. But you might now think, well, if the victim and the attacker are on the same CPU, then from a security standpoint, I've already lost, right? I'm running him on my machine. So what's the issue here? Well, this works across a sandbox. So if you're thinking you're running code you don't control all the time in your browser, because there's probably JavaScript enabled, and you just download that from the server and run it on your machine, and you trust that sandbox to keep it from doing anything dangerous on your machine. But with these cache attacks, you can actually bypass these limitations of the sandbox and get access on a victim process that is running on the machine. Even worse, this works across process boundaries. So even if I have a process that has low privileges, this can be used to spy on the data of a process running with higher privilege. Even worse, this works from inside a virtual machine, because still you are running on the same cache, and it doesn't matter whether or not you're in a different process or inside the virtual machine, right? And then if you're thinking about virtual machines, you might go like, oh, but I'm using something like virtual machines, which is called Docker or whatever, and it's running somewhere in the cloud. So is that an issue? And of course it is. So if you can coerce the hosting provider to put the attacker virtual machine on the same cloud server as the victim virtual machine or Docker image or whatever, then you can just do this on the same machine. You are running on the same CPU. And as a victim, it's pretty difficult to protect against this, because you may not be in control of how the cloud provider allocates the machines to the different users. And what makes this even worse is that because the actual application still is running, it's maybe running a little slower because it has more cache misses, for example. But apart from that, this attack is completely transparent to the user. He doesn't notice anything, even though his data is being infiltrated via the side channel. So I've put some more info over there at the bottom. Meltdown and Spectre are also using caching to exfiltrate data across boundaries like sandboxes or processes, and have been very widely reported about in the press a few years back. Now let's go to the area of power consumption. This is something that is not new, and the basic idea is to get very fine-grained regarding time resolution power consumption information about your victim device. So you see on the bottom left how such an attack might look like. You have a victim device, you attach some cables to the power supply of the victim device, and then you measure with an oscilloscope or similar, you measure the power consumption over time. And if you can then compare the power consumption of processing a certain key then with some known power consumption for that device, then you can figure out, oh well, this matches if I use a key byte of 0.1, and it doesn't match the power consumption if I were using key byte 0.2, and then you kind of just incrementally disclose the key, for example. So at the right you see an RSA, an AS encryption process, where you can very clearly see how the different steps of the algorithms are executed one after another. And if you just get enough power traces of the same or different encryptions, then you can use that to disclose the known secret key used in that encryption or decryption process. Very similar is electromagnetic side channels. So those are also on a very low hardware level. And I've actually brought an example of such an attack. So at the right, you see a device that is not connected to the oscilloscope on the left, but you see the antenna. And what actually happened here is that the internal connection between the display and the CPU was long enough that this emits electromagnetic radiation, and that electromagnetic radiation can then be detected by the antenna being placed considerably close by. And then essentially you have to compare for different pins that are for different numbers that light up on the display. You just have to compare that to the electromagnetic radiation you got, and you can then kind of tell apart different numbers just by the electromagnetic radiation that you receive. Last but not least, we should cover the optical side channel. So shoulder surfing, or just looking at someone's screen while they type the password, is a very viable attack. And should not be underestimated, although it's probably not that interesting for us from a cryptographic perspective. But there are uses of this, for example, with infrared imaging, where you can kind of figure out what the password somebody typed, or the pattern they swiped on their Android phone or iOS phone. By taking an infrared picture of the screen after unlocking, and then you can kind of see where the finger has been for how long, and see a pattern by just seeing the body heat on the glass of the display. And then let's come to a very interesting area. It's also one of the oldest side channels. And I'm not talking about listening in on people's conversation, but for example, typing on a keyboard makes some sound, and different keys on a keyboard make slightly, very, very slightly different sounds. And that has reportedly actually been used to attack people by some spy agencies that put microphones in or very close by to typewriters, for example, and then they could get the password or the secret information from somebody just by listening. Then there's a very interesting avenue of research where people figured that electrical components emit ultrasound based on how much current is flowing through them and stuff like that. So that can also be used to attack cryptographic implementations on a very low level. And on a very high level, you have to consider that printers are loud. I guess everybody knows how loud a printer can be, especially dot matrix printers. And you can also do some statistical analysis on the sound coming from the printer, if you record it with a hidden microphone somewhere, and then also deduce what kind of number or letter has been printed. So this is very practical against dot matrix printers, which are still commonly used in banks, for example. And they're just listening in on the printing sound can also be used as a side channel for what has been printed. And then there's an attack going far back into the 50s that reportedly the MI5, the British intelligence agency, launched an attack on encryption machines. So those were mechanical encrypting machines. And they implanted microphones in them or close to them and listened on the sound of the user turning those wheels to set his encryption or decryption password in a way. So by listening to the clicks of the machine, they could then determine what the password was that was being used, and then use that to decrypt the message that was being sent and that they had intercepted. So that's one of the very first side channel attacks that we know about. Now, when I say that we know about, you can already guess that this probably is not an exhaustive list. I've tried to search for everything that was out there on the internet, but probably there's side channels that some intelligence agency is exploiting right now that the academic community does not publicly know about. And there's probably also stuff that is already there, but that nobody knows about. That is just waiting to be discovered, that, oh, well, we can also do this, use this cool technology to get some new side channel information from a device. And I guess that's also something that you can take away from this, that there's so many different ways in which your devices are emitting some information that we will always have some new way in which this can be abused, some old ways in which which might have been fixed in the meanwhile. But probably you can expect there to always be some cool, clever trick to do this in a new way. So let's come back to a short summary. We have seen what side channels look like, what an attacker can do with them. But now it is time to also take a look at how we can avoid them in the first place. So some very practical advice. For example, if you are trying to prevent Bleichenbacher or Manger style attacks, just be aware that side channels exist. And that means, for example, not leaking details, especially through error handling, because this is one area where a lot of things can go wrong and can be abused. If you're checking the plaintext structure, so something that you already decrypted, then if you need to do that, because for example, your padding requires that, at least check it thoroughly. Bleichenbacher's attack was so devastating because people usually just checked whether the first 2 bytes were matching. If they had enforced the whole structure of the padding, which means an appropriate amount of non-zero bytes following after that, and then a 0 byte as a delimiter, and then the actual message, then exploiting the oracle would have been way harder. So if you have some requirement on the structure of what has to be there, which value has to be there, at least check all of it. You might be thinking, okay, I can just protect against, for example, timing side channels by adding some random delay, but that does not actually work, because you're just adding some variation to the timing, but the underlying differences in what takes longer and what takes shorter is still there. So you make it a little harder for an attacker. He just has to send a few more messages to kind of smooth out your random waiting delays. Next up is speed optimization. While it is desirable to a certain degree and also necessary, there are some optimizations that are very prone to being abused. RSA with the Chinese reminder theorem comes to mind, or where you're using sliding windows, and there it's very easy to leak your information through timing, because essentially you want to do less work, and if that means that in some cases where everything goes right, you're way faster. In the case of RSA CRT, you even leak how many ones were in your key, essentially, because you do some work for ones that you don't for zeros. And stuff like that is very, very difficult. So in general, try to do all crypto in constant time. So this is always desirable, so that you leak no information at all at an attacker, even if it means that in some cases you need to spend more time computing. But in the end, crypto is all about being secure and not about being blazingly fast but insecure. And then the next obvious advice would be just try to design your crypto system in a way that creating a side channel accidentally, or not checking something that absolutely needs to be checked, that this is not easy to do, that maybe it's inherently prevented by how your design works. And that means that any decision you make based on secret data, on plain text, for example, structure, is dangerous. And if you can design your system in a way that it does not do that, then also it's not that easy for an incompetent programmer, for example, to create, maybe accidentally, a side channel that leaks that information. And then in the end, even though it might appear now that side channels are everywhere and that they're a very dangerous thing, you also need to consider that some side channels are more useful than others. For example, a side channel with an error message being sent over the network is very easy to exploit on a big scale, whereas something like differential power analysis, where I need to have physical access to the device that I'm attacking, that I kind of need to take apart to be able to measure the power on the required level of detail, that is something that you probably don't need to be worrying about too much. Now, some programming tips. If you are implementing crypto and you do something like checking a message for proper structure and if everything is there, then just use, well, this is one way to do it, just use a variable like error, a Boolean variable that you initialize with false. And if it's true at the end of the function, then you throw some kind of error. But during the function, just check everything as if the previous steps had been successful, and just set the error to true and continue if anything is wrong. That ensures that the actual runtime of the function is the same, even if an error happened early in the function in the checking. That means you do some of the processing even though you don't need to, but it ensures that you don't leak the information of what went wrong to an attacker. If you have to, then you can kind of replace the message you got with some, for example, pre-generated random content if what you got is not suitable. So, for example, in TLS, it's a good idea to just continue with a random symmetric encryption key, even if your key exchange fails, because you don't tell the attacker that something went wrong during the key exchange, but it will fail later in the key exchange when that key is actually used, because well, it was garbage, and whoever attacked you will not get any information out of it. So that is also one way to address the issues like that. And yeah, very importantly, do not try to return early if you encounter something that is weird, because that will definitely tell the attacker, oh, he replied with an error way faster than expected. I know at which step of the processing the input was weird. Finally, let's take a look at what I am currently doing in my research, which is applying machine learning to side channels. So this has already been done before, especially in the area of differential power analysis, where you get a lot of data, more than a human could possibly take a look at every single data point. And humans are good at spotting patterns in that, but that tedious work can also be done by statistical analysis. But what I think is even more desirable is to have some machine learning that takes care of that, so that you can kind of just take a device and check whether it's susceptible to something like that, using machine learning. The end goal is to have something that kind of looks at Bleichenbacher style attacks, where messages are going back and forth through a network, and just try to find some patterns in there that distinguish valid from invalid inputs, for example. And that's what I'm going to be working on. That's why I gave this lecture on side channels in the first place. And if you happen to be interested in working on this together with me, then just send me an email, and we can talk about further options in that area. So with that being said, thank you for listening. Goodbye.